Okay, the last section we're covering in chapter 10 and is 10.3. And we're going to look at another type of sequence, and this kind is the geometric. Okay. Along with that, we'll look at the sum of these geometric sequences, and then I'm questioning whether we do the series. I don't think we do the series, unfortunately. I'm looking. Yes, we do. We do the series. So that'll be a lot of fun. All right. Right. So what is a geometric sequence? And our exploration will be very similar to what we did with the arithmetic version of this problem. Basically, the recursive formula, all you're going to do is multiply the previous term by some factor. Okay, and we're going to call that guy the common ratio. Okay, so to get to the next term of your sequence, just multiply the previous by some number, and the number is called the common ratio. Okay, so for an example of this sequence, we have 1, 2, 4, and it looks like I'm just adding 2, but no, 8, 16. So every time to get to the next number, you just multiply the previous one by 2. Okay? So 16 times 2 is 32, etc. Okay. Let's see what the book has for us. So problem 1, a sub 1 is 5, and the ratio is 3. And they want you to produce the first 4 terms. So a sub 1 is 5. A sub 2 is 3 times 5, 15. A sub 3, 3 times 15. And a sub 4, 3 times 45. This is 135. Okay. Another way you can think of this, and what we're headed towards, is finding, again, a nice general form such that if I want to know what a sub 80 is, I don't have to sit there and iterate them all. Okay, so I'm looking for a general formula, and you can get a hint at what that general formula is by looking at these in their factored form. So 5 is, of course, just 5. But 15 is 3 times 5. And then 45 is 3 times 3 times 5. And then 135 is 3 times 3 times 3 times 5. Okay. So it seems that instead of adding in every time like 2D and the next one plus 3D and then plus 4 times the common difference, this time we're multiplying in extra ratio. So this will be 3 to the first times 5. This will be 3 to the second times 5. This will be 3 to the third times 5. And what we're suspecting is that the formula will be something like the ratio raised to the n minus first power times some number, and a sub 1 is probably the number. Okay? Okay, so that's just foreshadowing where we're headed. Let's look at number 4, and we have another geometric. So a sub 1 is 24, and then the common ratio is 1/3. Right, so I need to multiply it by 1/3 every time. A sub 1, of course, 24. A sub 2, 24 times 1/3 is 8. A sub 3, 8 times 1/3 is 8/3. And of course, a sub 4, 8/3 times 1/3 is 8/9. Oh, sorry, I wasn't using this crud. Yeah, those are right. Those are fine. Okay. All right, so next we're looking now for this general term for the sequence instead of the recursive definition. Okay. So section 2, the general term of a geometric sequence. And again, we can iterate this formula. We can say a sub 1 we know is a sub 1, and then a sub 2 is a sub 1 times r. And then a sub 3, we take this thing and multiply it by r again. So we'll have a sub 1 times r, which will write a sub 1 r squared. A sub 4 is a sub 1 times r squared times r, which of course is a sub 1 times r cubed. And then hopefully you start seeing the pattern, right? So a sub 5, I think, is a sub 1 times r to the 4th. And in general, a sub n, I believe, is a sub 1 times r to the 1 less than n, right? So if this is 5, this is 4, if this is 4, this is 3. When this is 3, this is 2. So when this is n, we want n minus 1. Okay, and yeah, this is going to turn out to be the formula we want. And we can use it to determine, the 100th term of a geometric sequence, and that's what they want you to do in number 12. In particular, they want a sub 12 given a sub 1 is 4 and r is negative 2. So they want a sub 12 is, I don't know. They just want the 12th term of the sequence. So a sub n then is equal to a sub 1, which is 4, times r, which is negative 2, to the n minus 1. Okay, so in this case, a sub 12 is what we're after. So you just plug 12 into the formula. 12 minus 1 is 11. Negative raised to an odd power is negative. So we're going to add up with a negative answer. 4 times 2 to the 11th is going to be negative 8192. Okay, let's look at other variations on this theme. Number 21, they want you to find the general term formula and then find a sub 7. So they give you the sequence. And to find the r term, you remember in in arithmetic context, we would subtract 2 consecutive terms. Now we're dividing 2 consecutive terms. So r is always going to be a sub n plus 1 all over a sub n. So you take negative 3, or you take 6, and then divide it by negative 3. Or you take negative 12, divided by 6. So you take negative 3, divide it by 1.5. Let's take negative 12 over 6. So r is going to be negative 2. The nth term formula then is a sub 1, 1.5, times r to the n minus 1. The book wants to know what is a sub 7. So you just plug 7 into this formula. Negative to an even power is positive, so we'll have 2 to the 6 times 1.5, and that'll be 96. Keep going. So I got 24. Kind of an odd looking one. 0.0007, negative 0.007, comma 0.07, comma negative 0.7, comma dot dot dot. And then we want to do our common ratio. So we need the r term, the r factor. So take 2 consecutive terms and divide them. I'll just take the later ones, negative 0.7, and divide it by 0.07. Okay, so this will be negative. And if you multiply top and bottom by 100, you'll get negative 7 all over 70, which is the same as negative 1/10 which is negative 0.1. Oh, whoops, did I do that the wrong way? Yeah, sorry. This would be 70 and this would be 7. So it's just going to be negative 10. Sorry. Okay, so the a sub n, the general term formula then is going to be a sub 1, which is 0.0007, times r, which is negative 10 to the n minus 1. Okay, and then they want a sub 7, so a sub 7 is 0.0007 times negative 10 to the 6. Okay, let's figure out what that is. And that's 700. Okay, now we want to start adding the terms of the geometric sequence together and find a nice formula for that, like we did with the arithmetic sequence. And the formulation of that is going to be very similar. So we're going to add it to itself, basically. So the sum of the first n terms of a geometric sequence. Okay, so let's take a look. S sub n is going to equal a sub 1 plus, and then you always multiply in r to get to the next term. So a sub 1 times r plus a sub 1 times r squared plus a sub 1 times r cubed plus dot dot dot. And then a sub 1 times r to the n minus 1 will be your last term. Because look, this is r to the 0 power, r to the first power. The third term is r to the second power. The fourth term is r to the third power. So the nth term must be r to the n minus 1 power. Then we're going to multiply it through by r and add it to itself. So r times s sub n. I'm distributing r to every one of these terms. So a sub 1 times r is, and I'm going to rearrange my sum. I'm just going to push it over a little bit. So when I add them up, they're going to have like terms, so to speak. A sub 1 times r is a sub 1 r squared, etc. A sub 1 r squared times r is a sub 1 r cubed. And then a sub 1 r to the n minus 1 times, well, we need to multiply the previous one. A sub 1 times r to the n minus 2 times r is a sub 1 r to the n minus 1. And then the last one is r times this thing. Let's zoom in on that and see what that is. R times a sub 1 times r to the n minus 1. Okay, we can rewrite that using the commutator property of multiplication. So a sub 1 r times r to the n minus 1. And then to add, or to multiply like bases, you add the exponents. Okay, so you'd have a sub 1 r to the 1 plus n minus 1. And then 1 plus n minus 1 is r to the nth power. Okay, so when you multiply this term by r, you're going to end up with a sub 1 r to the n. Oops, and we don't want to add them, sorry. We're going to subtract them this time, so it's a little bit different. And what happens when you subtract them? Well, let's look. I'll have on this side s sub n minus rs sub n. On the other side, you'll have a sub 1 minus 0 is a sub 1, a sub 1 minus a sub 1r minus a sub 1r. Well, that is just 0. So what's occurring is this huge cancellation of terms. right, all the way up to here, and then you'll have minus a sub 1 r to the n. Okay. The next thing to do then is to solve for this s sub n. I need a nice formula for s sub n. So I'm going to factor s sub n out of this. On the other side, I'm going to factor out the a sub 1. And then I'm going to divide both sides by 1 minus r. And that'll give me my nth term formula for the sum of the first n terms of the geometric sequence. Okay, so let's apply this to problem 27. And they want you to find the sum of the first 11 terms. In other words, find s sub 11 of 3, negative 6, 12, negative 24, etc. Okay, so to pull this off, I need a sub 1 and I need r. So a sub 1 is easy, that's just 3. To find r, you take the ratio of two consecutive terms, right? So r, I can say, is 12 over negative 6, for instance. That'll be negative 2. And so s sub, what do we want? 11 is equal to 3 times 1 minus negative 2 to the 11th, all over 1 minus negative 2. Right, and these are kind of a nightmare to put in your calculator. We clean it up a little bit. So you have 3 times 1. Negative to an odd power will still be negative. So you have 1 minus negative something. So it'll be 1 plus 2 to the 11th, all over 1 plus 2, which is 3. So it'll just be 1 plus 2 to the 11th. When the 3's divide away. So 3 over 3 is the same as 1 over 1. So we have 1 plus 2 to the 11th, which is 2049. Okay, so good stuff. Let's look at other variations from the book on this, and then we'll look at an application. And then we'll look at the geometric series. Okay. So let's look at, I guess, 35. And we want you to figure out this sum. So they give it to you in summation notation. I equals 1 to 6, I guess, of 1/2, and then I plus 1. Okay. So I'm going to expand it and see just what I'm dealing with. And then I can kind of figure out what is a sub 1, what is my r, and so forth. So when I plug 1 into this formula, I'll get 1/2 to the 1 plus 1. In other words, 1/2 to the 2. So 1/2 squared. And then plus 1/2 to the 2 plus 1, which is 1/2 cubed. And then all the way up to plus 1/2 to the 6 plus 1, which is 7. Okay, so my sum is 1/4 plus 1/8 plus dot 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 all the way up to plus 1 all over 2 to the 7th, which is, well, let me figure out what that is. 2 to the 7th is 128. Okie dokie. So what do? I need to figure out what my a sub 1 is. That's just 1/4. I need to figure out what r is. So for r, you just take two consecutive terms and make a ratio. So I'll have 1/8 divided by 1/4. In other words, 1/8 times 4 over 1. To do division, you just multiply by reciprocals. So this will be 4 over 8, which is 1/2. So the r value is actually 1/2. So our a sub n formula, if you need that, I don't think we do, but if you did, it would be 1/4 times 1/2 to the n minus 1. Okay, so anyways, what we want is the actual sum of the first 6 terms. So if you look at the index, we're going from the lower limit 1 to the upper limit 6. So you count them on your fingers, 1, 2, 3, 4, 5, 6. So it must be S sub 6. And that'll equal A sub 1, which is 1/4, times 1 minus R, which is 1/2, to the 6th, all over 1 minus R. So what is that? Well, that'll be 1/4 all over 1 minus 1/2 to the 6 is 1/64. 1 minus 1/2 is 1/2. So this will be 1/4 times 63/64 times the reciprocal of 1/2, which is 2. Okay, so this will equal 63 over 128. Okay. Right, so the next, let's go ahead now and look at an application. And again, we'll talk about salary. Sorry, one second. So salary. So if you take like a business math, all this stuff will kind of keep popping up again and again. So 4 applications in particular. First, we'll look at salary. I don't know if we'll look at anything else, but salary. We'll look at number 67. If you're following along, it's on page 174, 1074. What does it say? Professional baseball player signs a contract with a beginning salary of $3 million for the first year and an annual increase of 4% per year beginning in the second year. That is, beginning in year 2, the salary will be 1.04 times what it was the previous year. What is the salary, the athlete's salary for 7 years of the contract, round to the nearest dollar? Okay, so the starting amount after 1 year is $3 million. And then this person is getting 4% more every year. Okay, so the sequence, or maybe we could think of it as a sum, is going to be $3 million, 1, 2, 3, 1, 2, 3, plus $3 million plus 0.04 times $3 million and then plus whatever. Okay. So what is this? This is 3 million plus, we could factor a 3 million out of these terms and we get 3 million times 1 plus 0.04 plus whatever. So our sum is 3 million plus 3 million times 1.04 plus ... Okay. In other words, A sub 1, of course, is $3 million, but R is the ratio of 2 consecutive terms. So all we have to do is take this and divide it by this. Okay. Zoop, zoop. And we're left with 1.04 as our R value, our ratio value. Okay. And that's what the book says. The book says that is, beginning in year 2, the athlete's salary will be 1.04 times what it was in the previous year. So there's that 1.04 thing we're talking about. Okay. They want to know what the salary is going to be in year 7. And so, in other words, they want S sub 7. So we can figure that out quite quickly now. S sub 7 must be equal to A sub 1, which is 3 million, times 1 minus 1.04 to the 7th, and then divided by 1 minus 1.04. Okay. And pop that into your calculator and see what you get. So 3 times 1 minus 0.04 to the 7th. This is all divided by minus 1.04. And I'm getting 2.36949 times 10 to the 7th. Let's see what that is. 1, 2, 3, 4, 5, 6, 7. So it's 2369490. So $23 million basically for the 7-year contract. Okay, so is that what they wanted? Oh, no, they just wanted the actual salary in year 7. So that salary in year 7 is a little easier to find. That's just a sub 7. So our n term formula for a sub n is just going to be a sub 1 times r to the n minus 1, which in this case is 3 million times r, which is 1.04 to the n minus 1. So a sub 7, what is he making in year 7? That's just going to be 1.04 to the 6. So let's find what that is. 3, 1, 2, 3. 1.04 to the 6. 3.79596 times 10 to the 6. So 2, 3, 4, 5, 6. This equals 3795960. So $3 million, almost $4 million in year 7 is what this guy's making. But the actual sum of the salary over 7 years would be that $23 million. Okay, let's look at another. So this is now 73. A job pays a salary of $24,000 the first year. During the next 19 years, the salary increases 5% each year. What is the total lifetime salary over the 20-year period? Round to the nearest dollar. Okay, so the job pays, and we consider that our first value, a sub 1, is $24,000. And then it's saying during the next 19 years, the salary increases 5% each year. So again, you can think of it as, okay, the first term is 24,000 plus, we have 24,000 plus 5% of 24,000. Okay, so that's going to equal 24,000 plus, you can factor the 24,000 out. You get 24,000 times 1 plus 0.05. And then that'll equal 24,000 plus 24,000 times 1.05. And then we could factor out the 24,000, and we get 1 plus 20. Sorry, we already did that, right? So what we want is the R value out of this. So you take these two terms and divide them. And it's kind of like a pattern at this point. You know it's going to be 1.05 from the previous problem. Whoops, 24,000. So yeah, the ratio 1.05. We want to know the salary over 20 years, 20-year period. So basically they want S sub 20. And what is that? Well, it's A sub 1, 24,000, times 1 minus R, 1.05 to the 20th, all over 1 minus 1.05. I'll put that into our calculator and probably have the answer. I'm getting $793,583. Okay. Right. Okay, the final thing we want to deal with then are these geometric series. And these are sums that add up and up forever and ever and ever. And you may be wondering, well, how do I know it's actually going to equal something? How can it equal something? So for instance, if I added 1 plus 2 plus 3 plus 4 plus forever and ever, what does that equal? Does it equal anything? Something like this doesn't equal anything in actuality, but something like this, 1 plus 1/2 plus 1/4 plus 1/8 does equal something if you kept going on and on forever. Okay. So how is that? How does this thing, well, you can think in terms of boxes with areas. So I'm taking a box with area 1, and then I'm adding to that a box with area half of that. Okay, so I'm going to add in a box with area that is half that original area. And then I'm going to add in a box that has 1/4 of the original area. In other words, half of this area. And then you add in a box that has half of this area. And then a box that has half of that area. And then a box that has half of that. And you just keep on going on and on forever. And you see you're never really going to exceed this region here, these two boxes. So you may even say, hey, I think the final area is just going to be 2. Because if this side is 1 and this side is 1, the area of this is 1. The area of this entire thing is 2, we think. Okay, so is that true? And it turns out there's a nice formula for this. And yeah, in this case, it is true. Okay, the sum of this thing, which they'll call a series, is equal to 2, believe it or not. Okay, so anyways, let's make that a bit more exact. So this is section 5, a geometric series now. And what are we looking at? We're looking at an infinite sum. So I'm going from I equals 1 to infinity. Okay. And then we have a sub 1 r to the I minus 1. And if we wrote that out, we would see the geometric sequence being added together infinitely. Okay. So we would have a sub 1 r to the 0 plus a sub 1 r to the 2 minus 1, which is 1, plus a sub 1 r to the 2 plus da 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 plus a sub 1 r to the n plus da da da, on and on forever. Okay. So from before, we noted the nth partial sum, the sum from I equals 1 to n of a sub 1 r to the I minus 1, which we were calling s sub n, this thing here. We had a formula for this. We said it was a sub 1 times 1 minus r to the n all over 1 minus r. If r is actually the absolute value of r is less than 1, this thing, this object, will approach a value. Okay, this r thing right here, if we let, so if r is less than 1 and we let n go to infinity, then and we could write it in a funny kind of way, this notation that we'll see later in calculus, the limit as n goes to infinity of s sub n, which is actually just the limit of this thing here, this part of it, this r to the n part, will actually go to 0. Okay? And you'll just be left with a sub 1 all over 1 minus r. So there's a lot of questions here. Why does that thing go to 0? I can give you kind of intuition. If you have r equaling 1/2, and you think of real big numbers for n. So when n is 1, you'll have, of course, just 1/2. When n is 2, you'll have 1/4. But when n gets to something like 100, you'll have 1 all over 2 to the 100. And if you put that into your calculator, it's going to do what? Well, you can try it. 1 over 2 to the 100. You're going to get 7.8 times 10 to the negative 31. And so what is that? Well, that's 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 31 zeros, and then 7, 8. In other words, this thing is getting really close to 0, which is what we mean when we said this thing's going to 0. You can pretend it's equal to 0 when n is really big, because it's such a small number. Okay, so in the end, if r is some sort of fraction less than 1, like this case, you can do this infinite sum. You could take the s sub n and just keep extending it forever and ever and end up with a number. So going back to our initial example where I was talking about the box, 1 plus 1/2 plus 1/4 plus 1/8 plus dot, 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 we could rewrite that as a sub 1, which is 1, all over 1 minus the common ratio, which if you look in divide terms, r is going to be 1/4 over 1/2. In other words, 1/4 times 2, which is, of course, 1/2. We'll get 1 all over 1/2, and then 1 over 1/2 is 2, and that's exactly what I was saying back here. Okay. And all I did this time was use this formula here. A sub 1 all over 1 minus r. So a sub 1 again was 1 all over 1 minus the common ratio between terms. So 1/4 divided by 1/2 is 1/2. Okay, so pretty interesting stuff. We could do all kinds of neat problems with it. Let's look at 37. So we have 1 plus 1/3 plus 1/9 plus dot, dot, dot. We want to know what that equals, if it equals anything. And this time a sub 1 is 1, and r, you can go 1/3 divided by 1 if you want. So it's just 1/3. So at the end we have 1 all over 1 minus 1/3. So 1 all over 2/3. In other words, this is equal to 3/2. Let's look at another one. Here's 43. We have the sum from I equals 1 to infinity of 8 times negative 0.3 to the I minus 1. Okay. So we want to identify a sub 1 and then the ratio. So a sub 1 is 8 times negative 0.3 to the 1 minus 1 is negative 0.3 to the 0. So it's just 8. And then plus 8 times negative 0.3 to the 2 minus 1, so 1. So I just have 8 times negative 0.3. And then plus 8 times negative 0.3 to the 3 minus 1, which is 2, and then plus dot, dot, dot. So a sub 1 is obviously 8. The r value, you just take these two and divide them, and of course you just get negative 0.3, right? So it's 8 times negative 0.3 divided by 8, which is negative 0.3. Okay, so our answer then will be 8 all over 1 minus negative 0.3. It's kind of weird because the r value is negative this time, but that happens. This one was positive. This one was negative. So I'll have 8 divided by 1.3, or if you'd rather, 80/13. You could do some tricks with this, and one trick is converting repeated decimals into fractions. So example, problem number 47, we have 0.47 repeated. First, write it as a series, okay, a geometric series. So this is the same as 0.47 plus 0.0047 plus 0.000047 plus dot dot dot. Okay. Our a sub 1 value is 0.47. Our r value is, what the heck is the r? Take 2 and divide them. So 0.0047 divided by 0.47. Okay. I can multiply top and bottom by 1,000 or by 10,000 even, and get, let's just put it in the calculator. So 0.0047 divided by 0.47 is 0.01. Okay, so our sum, and all this is kind of just scratch work here. Our sum of this, well, what this repeated decimal will end up equaling is 0.47 all over 1 minus 0.01. In other words, 0.47 all over 0.99. If you multiply top and bottom by 100, you get 47/99. And of course, you put that into your calculator, you get 0.47 repeating. Okay, I think that's all we need to say about that.